Welcome to the third lesson of the course about the introduction to statistical physics with a computational perspective. And we are now dealing with the idea of integrating a Newton law, and this is the first step in our path. And to follow, to compute the evolution of a system possibly composed by many particles, but really we start with the simplest model, which is just one coordinate of one particle. And so we have to numerically compute the evolution of the second Newton law, force equal mass times acceleration, which is the second derivative of the position. And clearly the acceleration is given by the force that can depend on the position, velocity, for instance, friction, and time, divided by the mass m. And this has to be complemented with the initial condition of the initial position and the initial velocity. As usual, as we do when computing these things by hand using mathematics, we convert the second order equation into a first order system of two equations by introducing the velocity. And so we have this system with the same initial condition. For instance, let us start with a system that we know how to integrate theoretically. I mean the harmonic oscillator, which is a linear equation, that in 1D is just this one, and we know also the solution, which is this one. And so since we are dealing with the system of two equations, it is natural to consider the motion in the phase space RV, that in this case is just a two-dimensional space XV. And if the force does not depend on time, from each point, so since the motion is given only by R and V, from each point only one trajectory can originate, and so they cannot cross unless in the limit of infinite time. For instance, if I have some damped motion, two trajectories at the end can meet, but only in the limit of infinite time. And moreover, if the force changes sign with the velocity, so trajectories are also reversible. I mean that if I take one point in a certain point and I reverse all velocities, then the motion should go backward in time and reach the same initial point. Clearly, this is the case of conservative forces, for instance, not friction, but we can also have forces that depend on the velocity, like, for instance, Coriolis forces in mechanics or Lorentz force in electromagnetism. Actually, these are forces that do not do any work, but they can change the direction of velocity. Okay, so let's come back to the original harmonic oscillator. In this case, we know how the trajectory should appear in the phase space. They are ellipses because essentially they are the expression of the energy, kinetic energy plus potential energy, they are constant, they are sum. And actually, if we derive this expression with respect to time, we get back the Newton law. And so, well, transforming the system, we have just this expression for the phase space. So phase space is partitioned into ellipses. The motion is conservative, and clearly the ellipses are followed in this way. We start from, say, from here with a positive velocity, so velocity decreases, but the space increases, and then it arrives at a certain point. And so these are the oscillations of the harmonic oscillator, and that's all. Okay, now another way that we shall take into consideration of considering the evolution of the system is that they're not just following one trajectory, but a bunch of trajectories. If the system is nonlinear, so this does not happen for the harmonic oscillator, but if the system is nonlinear, then at a certain point the initial bunch of trajectory will spread all over the accessible space. And so, speaking about distribution that we shall meet in a future lesson, but we should be prepared to pass to statistical description. I mean, description in terms of how what is the probability of finding the trajectory in a certain point, so about the probability distribution. And this is one of the first steps. It says that for almost all systems, because almost all systems are essentially nonlinear, we should expect that, in some sense, regardless of the initial condition, at a certain point, that will be defined better in the following, we should be able to find the trajectory in any place, regardless of the initial condition, but according to the conservation law, for instance, conservation of energies. In this case, we can see that we have a double well potential. We start with a bunch in the phase space. It means that there is a certain distribution of energy. They cannot cross this energy barrier, so they cannot reach the other minima, but they spread in this interval of energy, so at the end they occupy all possible energy, and we shall try to model something similar to this. Okay, so let's come back to the Newton law. We have to integrate this in numerically. So since computers are not humans, then we cannot follow the usual technique of finding, of searching some analytic solution. Rather, we have to replace derivative with some approximation scheme. The first one comes directly from the definition of derivative, and so we have just to consider that f times t plus delta t regarding this limit is just the function times t plus the derivative times delta t. So this is called the Euler integration scheme. It is not clearly the most accurate, it is just the first approximation, but sometimes it can be used just to have an idea of what is going on, especially if the system is spatially extended, so we need some method which is fast and economic in order to to have some idea of what is going on. And so for the harmonic oscillator, this is what we get. And so we can use NetLogo to explore these things. So let us go to this interface. We shall come back to the code after that we have a look at the interface. So we start by drawing some axes, and then we can start a new trajectory from a given point that I mark with an X. It goes running for a certain amount of time, and it ends here after this time, elapsed time, and it is marked by this dotted where it stops. And so you can see that actually we have a certain ellipse governed by this k, which is essentially omega squared. The mass is 1. So if I change this, I have different ellipses, and okay. So, but the important point is that actually energy is not strictly conserved, since it increases. Instead of being an ellipse, it is a kind of spiral. Clearly, I can reduce this increasing of energy by reducing the delta t, but since the number of steps is essentially the time divided by delta t, the cost of having a higher precision is that of using more computer power. Clearly, this is nothing for computing the evolution of an harmonic oscillator, but when we deal with the system composed by many particles, this can be the crucial point, as we shall see. And so let's have a look at the code that you can download from the web page. Actually, most of this setup is just to draw these two arrows. So essentially, I define a couple of turtle, one which is invisible here, and one here with this shape, and this is a link. Another possibility is that of having a turtle here, put pen down, and draw this up to here. But this is not really the important point. The interesting point is this one, where I wait here while not mouse down. So essentially, all this is is waiting for a mouse down here. So when I draw trajectory, I just wait. You see that the cursor is waiting until I click. This is not the only position. I could also have done an infinite loop button and process all this if mouse down. This is the alternative. So I wait until mouse is down, and then I create one turtle, which takes the shape of an X. Actually, this is the turtle that stays here, and this is a turtle that do not move. And okay, I set the size, then it places this position where I clicked, and this turtle creates another turtle. The method used from a turtle to create another turtle is to hatch. It's clearly the term used for birds. So they hatch another particle, one particle, that takes the shape of the circle, and this is essentially the ones that ends the trajectory, and certain size, certain mass. It has a pen down, so it leaves the track here, and then there is the time loop, where I take the coordinates, I compute the force with this report here in order to have a flexible system. Actually, I can simulate all one-dimensional system just changing the report here. And while, so I increase the time here. Unfortunately, NetLogo has no force, so I have manually to let set the time to 0 and then increase the time. And so I compute the force, I increase the x, I increase the v according to the equation. I check if the trajectory is still inside the loop, otherwise it stops. Actually, I can mark the crash, just to make this clear. I can say, for instance, set shape star, set size 1, so it is larger. So let's check. If I start a new trajectory from a position where the trajectory exit from the world, I say I can mark the crash with the boundary somewhere and stop the evolution. Otherwise, it continues to run. And clearly, if I start with a very large delta t, what happens is that the trajectory starts to grow its energy until it crashes at the boundary of the world. Okay, let's save. And that's all. So essentially, the Euler scheme has this drawback, which is not always so. It depends on the system, because we can have a look at what is going to happen in this case. So this is again the idea that during time energy increases. The fact is that we can visualize this drawing several surfaces of energy, and one can see that actually we compute the derivatives here and increase the position by a small amount. But since due to the form of this surface energy, so this is not true for all surface energies, this brings the trajectory inevitably on another say ellipse at higher energy, and again here we have to compute the energy, so I go to another surface of energy and to another, and so on. So for this particular shape of energy, Euler scheme inevitably causes increase in energy. A way of curing this drawback instead is that of separately increasing the steps of x and v. For instance, I'm here, I compute the derivative here, but I just increase, say, v. So I go on this new surface. Then I again compute the increase, the derivative, which is this blue arrow, but I only increase the x. You can see that I am now closer to the initial energy surface, much closer than in the previous case. And this is the error that I would do with a simple Euler scheme, while here I'm doing a much smaller error. So I can separately increase the x and v. It is the same also if I increase first only the x, and then only the v. And this scheme is called the leapfrog. Actually, it is a first order approximation that behaves much better than the Euler method, and we can have check directly with NetLogo. So I can open the not this, the other lesson 3, leapfrog, harmonic oscillator leapfrog. So I draw again the system. It is essentially the same as before, but now you can see that even with a fairly large delta t, energy is quite stable, and I can check this with different values of omega. You see energy is quite stable. Actually, you see that the trajectory is not really a symmetric ellipse, it is slightly tilted, because clearly this is still a first order method. And for instance, I could add a plot just to monitor the behavior of I don't know, the energy or the x or the y. Let's check the energy. So energy, and I'll update this by the program. Okay, so let's go to the program, and here when I compute x and v, I can add say let key m times v squared divided by 2 plus k times x squared divided by 2, and then I can plot k. Since I have just one plot, I don't have to select which plot I'm using, and there is already a global variable called k. K clearly, because since the computer netlog does not distinguish between lowercase and uppercase, I have to use another value. Okay, I can check now it is okay, and let me see if this works. Okay, so you can see here that actually energy is fluctuating, but the important point is that you can see here that it fluctuates but stays in average constant, and this is one important point in simulating, because I don't want to have an unstable system. Okay, so we can also produce this new plot. So I may save this new version so that you can find it on the web page. Clearly, if I reduce the time interval, I get less oscillation, and the curve is much more symmetric. Clearly, this has the cost of increasing the number of time steps. Another alternative, instead of increasing the number of time steps or decreasing delta t, is that of using more accurate methods, which implies computing more times the derivatives. So essentially one has always this drawback. If one wants to have higher precision, one has to spend more computed time, either lowering the time step or increasing the number of times I compute the function, the derivative. One good compromise is velocity Verlet. Velocity Verlet is a kind of, so leapfrog is a kind of first order velocity Verlet, and this is the second order. The idea is to advance a half time step the velocity, compute the position, compute forcing according to the position. This works only if the force depends only on the position. And finally, compute the other half time step for velocity. And now we can use a big delta T for computing energy, which again fluctuates. So let me take the NetLogo program of the harmonic oscillator with Verlet. Then again, I can draw my trajectory. You can see that now I'm using a fairly large delta T. I can still add the plot of the energy here. Okay, I change. So let's have a look at the code, which is quite simple. In this case, I just advance a half step for the velocity. Then I can increase the position. Then I compute the force with these new positions, and then I finish advancing the velocity. At this time, I can compute the energy, which is not, before I made a mistake, this is not the kinetic energy, it is complete energy. So it is m times v squared divided by 2 plus k times x squared divided by 2. Then I can plot energy, and that's all. Okay, so I set up a new trajectory, and now I can have a look at this plot, and probably by increasing a bit the resolution, I can see that now energy still fluctuates, still oscillates, but much less, considering that I actually used a quite large delta T, and so okay, so this is a good news. So I had clearly I paid the fact that I now have to use a more complex code, but actually I'm only computing the forces once per time step, so it is a good compromise. And but now I have a much more accurate computation, and this is a fairly good compromise for having a good computed code. This works only if the forces depends on the position, not on the velocity, and for conservative system. So for other system, I have to use other technique that I shall show you in the following. Okay, so let's come back to the idea. Now, what is the motivation for because so let's stay behind the fact that a certain algorithm works and other not. So let's come back to the Liouville point of view. I mean, computing the evolution of a bunch of initial conditions. So now I have a certain algorithmic scheme that essentially can be seen as a discrete time evolution, and in mathematical terms it is called a map. So this map says that I compute x at a certain time t plus delta t, v at a certain time t plus delta t, or I can also say that time is computed in terms of delta t, and this is a function of x and possibly v at the previous time step. Now, the volume of a certain bunch of conditions is given by the determinant of this Jacobian matrix, which is simply composed by the partial derivatives of f and g. So you see that for the Euler scheme, we have this Jacobian, which is 1. So let's come back to the evolution of Euler, which is this one. So if I compute the derivative of this with respect to x, it is 1, and the derivative of v with respect to v, it is 1, while the derivative of x with respect to v is delta t, and the derivative of v with respect to x is minus omega squared delta t. So essentially, this is the Jacobian. Now, the determinant of the Jacobian gives the evolution of the volume in the phase space. And so you see that here, the determinant of this is 1 plus omega squared delta t squared. And clearly, the volumes are not conserved, and they always increase, as we have seen, and it increases at the pace of delta t squared. So clearly, if I make delta t small enough, I can reduce this increase, but I always have this increase. On the contrary, for leapfrog, I separately increase t, v, and x. So the Jacobian of one full time step is the product of the Jacobian for the two half step. One in which I increase, say, delta t x, so I have v per delta t here, and another one in which I separately increase v, so I have the minus omega squared delta t here. But now, the determinant of this product is the product of determinants, and you can see that both have determinant equal to 1, and so the volumes are conserved. And this is the idea of symplectic algorithms. Devise a scheme that allows to have conservation of volumes in space. Yeah, this works only for systems that need to conserve volumes in space, conservative systems. And for the second order velocity Verlet, the procedure is similar. I have half steps, and so I have now 3 determinants, but all of them have determinant equal to 1, and so the total is equal to 1. Okay, this is not a sufficient condition. I still need to have an algorithm that follows my dynamics, so I cannot simply have an algorithm that is arbitrary. I need an algorithm that is a good approximation of the original differential equation, but this is a needed condition for conservative systems. Now, we can have a look at reversibility. Reversibility is a good test for conservation of so for conservative systems, and we can check this using our NetLogo system. So the idea is the following. Let's start from, say, from a certain point, and let's use a small time amount. Maybe we can have it even less. Okay, so we start from here, we go for a certain number of time steps, and then we arrive at a certain point. Now I want to reverse the velocity here, so I reverse the velocity, and when I reverse the velocity, clear I'm going to the same position, but at the reverse point in the trajectory. Now I can go backward in time for the same amount of time steps, and this clearly goes from here to another point. I have problems with my monitors now. Okay, so I start now from here and I go backward in time. So essentially, it's the same way. I just go on with the same algorithm as before until I reach another position, and then I reverse again the velocities, and I get back to the position as to my initial position marked here. I already had the X, and I mark it now with a circle. So these points mark when I inverted the velocity, and clearly X marks the starting of the two trajectories, and so clearly I can, better if I set up, I can also go for a fairly large amount of time. I run, I arrive here. Now I reverse velocities, I run again a certain number of times, I arrive here, I reverse again the velocity, and I get back to the initial state. Clearly, this is true only with a certain position given by my algorithm. If we want to have a look at the code for reverse V, I draw a special turtle shape, which is the double arrow. Here it is. So I used this editor in order to draw a new shape, which is just for, say, marking with something sensible on the drawing, and this is my mark. And clearly I set a certain size, I set a certain heading so that it stays vertical. I could have chosen another orientation. Then and this is I use just a new turtle that do not move, and so I change the y core, which is V in our phase space. I mark again the point with another shape. I could have also used another way of labeling, but okay, this is an easy way. So I mark again the new point with an X, and which is another turtle that do not move. Then I again draw trajectory as before, and I mark again the new point with an inversion of velocity. And finally, I ask to take a new shape, which is an empty circle. This one, turtle shape editor. Circle 2 is an empty circle, this one. And okay, and then finally I change a bit the size so to have a large enough circle. And that's all for this model. And we can go back to our screen and continue with the illustration. Now we can pass to a nonlinear system, still integral, but nonlinear. One of the few ones, nonlinear systems that we are able to solve analytically, clearly using a special function. If I remember well, the Bessel function, but we are not interested in the analytical solution. So the idea now is that to replace the second order differential equation with a similar one, but where instead of x I have sinus of x, and again we have different meaning for this omega, but we are not interested in this. Okay, so we can play with the net logo. I open the new model here, pendulum dot net logo. Again, I have my system. It is all the same as before, except that I have a different form of the force. And so I can start a new trajectory, and I see that clearly if I start a trajectory, say, with in certain position, I could have started say, in position 0, but with a certain velocity, which is equivalent to say to have a pendulum and to start kicking it with a certain initial energy. I don't have it here an experimental system. I could have built one, but it is very simple. So it starts the oscillating. Clearly, if I give it a very strong kick, it simply goes turning around. If I reduce the kicking, I start seeing oscillations. Clearly, I can kick it in the opposite direction and start rotating in a different direction. But if I start it with small enough energy, I start seeing the real oscillation, which is a periodic motion, around 0. Clearly, if I kick it with a very, very small energy, I get back the framework of the classical harmonic oscillator, which is the approximation of the pendulum for slow energy. Clearly, I can also have change the frequency here, or increase it. So I have different patterns. Clearly, I could multiply everything by a certain amount. Now, let's study what happens for different initial conditions. You can see that according to where I start, I can have clearly oscillations around new centers. Essentially, this is due to the fact that the system is periodic, sinus is periodic, so I can start with the same kick but from a different position. And if I investigate carefully enough, I can see that actually there are trajectories that so that the phase space is divided into these deformed ellipses at various positions near multiples of pi, and oscillating so rotation with variation of energy at several initial conditions, and you see that there is a separatrix that separates rotations from oscillations here, and this separatrix is somehow the only trajectory that can cross each other. So if I am able to find a good approximation of this separatrix, you see that actually I could, in principle, start from here and reach this point, or start from here and reach the same point. Actually, this is true only for really infinite time. Actually, this position corresponds to the pendulum in the upper position, and clearly I can give it a, a particularly accurate kick so that it arrives to the vertical position, but this is only possible for infinite time, because clearly I have to arrive there with zero velocity in order to stay there in the vertical position, and if I give it too much kick, too much initial velocity, it starts to rotating in the opposite way. This is a rotation, and if I give it too low kick, I arrive here and come back. This is an oscillation, a libration, and so I have these separatrix. But since this is a nonlinear system, I can check the Liouville theorem. Okay, so I can create a bunch of trajectories, and I can see it evolving in time. I can increase a bit the speed actually just by refreshing less times this display, and I see that the trajectories start to spread around in the phase space, and after a certain number of time steps, they reach a distribution which essentially includes all possibilities of energy. Clearly, I'm integrating this so I can make some error in the energy, but actually the initial bunch have not the same energy. They are distributed at random, and so I can also ask turtles to put the pen down, so I can have a look of the trajectory, and you can see that they are distributed, say, on all, almost all possible energies. I start here again, and I see that so some of them have crashed here. They are distributed on all possible energies, and so this is the sense of the Liouville theorem that says that actually they behave like a drop of ink inside some liquid, so they disperse if the system is nonlinear, and because if it is linear, I can quickly replace this force with a linear force here. So now this is the harmonic oscillator. I have to say they are too high. I don't maybe this is the force of the spring, so I should increase. I don't know. Too much. Maybe we have to reduce it. Okay. Now you see that I have maybe still to reduce this again, and okay. Now you can see that for a linear system this does not happen, because essentially all have the same, all oscillations have the same frequency independently on the initial conditions, so they stay together. While for nonlinear systems, like for instance the much. Let me see. Reduce it. I have to reduce again the here. Okay. I have the distribution of oscillations without so on all the available distribution. Okay. So this is the essence of ergodicity. I mean that the system tends to occupy all available space, and we can also investigate another interesting aspect, since we have mentioned in the previous lessons the simulation of planets. So let's simulate planets here, and so we can investigate, for instance, Bertrand law or Bertrand problem, which is an interesting observation that among all possible central force, I mean forces that are directed from the, say, planet towards the sun, only two give origin to closed orbits. All the rest give rise to, say, kind of rosettas, and the only two are the classical planetary motion, so force that depends on the inverse square of the radius, and the harmonic oscillator, so forces that depends on the first power of the distance. All others give rise to rosettas. So we can check it numerically. So essentially the code is the same. I put very similar. I put just one planet in the circle just to mark the center, another planet with some initial conditions, some initial velocity, and delta t square, but I don't need it. And so I can remove this. And it was for another algorithm. So I first half of velocity, I advance positions, I compute forces. Forces I just need to compute the distance from the sun, and I can use the primitive distance. Then I compute the force. The force depends on a certain constant that can be determined here, and I take the power. So this is the power and the potential. So I increase the power by 1, and times the mass times d to the same power. I have to compute this in order to have the right versor, because essentially the force is vectorial, and when I take the gradient of this, I have the derivative of this that gives this, and then the gradient of r is the versor of r, which is the vector r divided by the absolute value of r. So in order to compute this, I need to compute this, and then to multiply, to compute the force by multiplying the value of the force times the vector, which is just x core, y core, while the energy is this to the power, to the some power. So check this, but I'm pretty sure that it works. And so you have also here possibility of adding other planets, but I have not done for this example. And then I increase the position, and finally computing all the energy, including also the kinetic energy. But we are not using actually the energy, but just to check if everything is staying good. Okay, so I can start with a certain velocity. I can fix here the power. So let's start with the standard planetary, standard Newton law for gravitational forces, and you can see that the planet follows the standard ellipse according clearly on the initial velocity. So if I increase a bit the initial velocity, I can have but too much, because now I have periodic boundary condition, but clearly this is not realistic. So I can increase a bit the velocity, not too much, so that I have nice ellipses around the planet. I clearly could also try to have almost circles like here, probably a bit less initial conditions. Yeah, this is almost a circle, and okay, so this is how things behave, and clearly delta t may be too much. I can also decrease delta t, so I have a more accurate projected, but it's also they are the same. And I can also check with the power 1, which is the harmonic oscillator. I think I have to decrease this constant in order to keep maybe I can increase a bit, not decrease to, oh, I can increase a bit this, also the spring constant. Let me see. Maybe I should increase more the initial velocity, and maybe reduce a bit this in order to have some ellipse. And so again, this is a closed ellipse. Notice that with respect to planetary motion, in this case, the center of the force occupies the center of the ellipse and not one of the foci of the ellipse. And okay, so this is the code. And now we can check that if I have even some power which is slightly larger than 1, and you can see that now the ellipse, this is the harmonic motion, start to tilt. The same happens if I have something which is, say, below 1. And I can check also near -2, so let's say probably have to reduce the initial velocity and increase the constant or reduce the constant. Probably I have to go back and increase a bit the time step in order to have a much faster algorithm. And you can see again that the planet now is not following a closed trajectory, but rather a kind of rosetta. This is for power -1.9, and okay, also for larger values of the exponent. We don't notice this because it is too, let's say, higher values of C, so that it is no more, it is more elliptical. And again, we can have different rosettas, but not a closed trajectory. Clearly, if we increase more the exponent, we can have also, let me see if I have to increase or lower this, maybe the initial velocity. And now I can also have a very funny trajectories, but they are not closed. And actually, when there were the first observation of the motion of Mercury, and they observed that the ellipse of Mercury was shifting beyond what was due to the known influence of other planets. And so one possibility that was explored was that the gravitational law was not modeled in the right way. Probably the gravitational law did not depend on the inverse square of the distance, but rather on some other power, until Einstein arrived and with the general relativity showed that there was the gravitation delayed the time, and this caused a different, so a precession, so a shift of the main axis of Mercury. Okay, so just to conclude, I would like to show a real example. In this case, it is the simulation of a multi-particle system, Lennard-Jones, the same that we have seen in the first lesson, but now not with the Monte Carlo technique, which is actually much simpler, but following the dynamics of the particle. So the Lennard-Jones potential is a potential that is well suited for simulating, so for approximating the potential between noble gases. So it is a spherical potential, so not suited, for instance, for water molecules or other molecules which are not symmetric. And it has an attractive long-range term that tends to bring molecules together, and a repulsive core, and it is modeled like this. So this is the shape. Epsilon gives the depth of the potential well, while sigma fixes essentially the equilibrium distance, which is this one, and the equilibrium distance is essentially 2 to the power 1/6 sigma, while this well is minus epsilon. And the force is given by the gradient of the energy, and this is the expression. And actually we can we scale all distance and times so that we just can neglect epsilon and sigma and have an expression in terms of the second inverse power of the distance here. So now the equilibrium distance is 1.122. And let's see, so clearly we can simulate, we can only take part of the extraction to see what happens. And the idea of molecular dynamics is that of integrating simply this equation of motion. And so the problem is that since each particle in principle interacts with all other particles, the complexity of the system scales like n to the inverse power, so n to the square, which is bad, because if you double the number of particles, you quadruple the time required, and so clearly quite soon we have the problem that we cannot simulate in finite time a large enough system. So the solution is that of truncating the potential after a certain point, in order not to have it going to infinity. And in general, it is truncated about 2.5 sigma or 3 sigma, where the potential you can compute what is the value of the potential at this point. And so the idea is to rescale the potential in order to have it going to 0 without any jump. This is important when you compute the energy, otherwise we see sudden jump of the energy simply due to the particle that crosses this distance. And so now we have this expression for the potential and this expression for the force, and that's all. And the idea now is to check which are the particles that can interact with a given particle, and it is done generally by dividing the space into squares or cubes, according if they are two-dimensional or three-dimensional, and to take into consideration only those particles that are inside the first neighbors of the cell in which the particle is. And you can compute that even in the dense packing of the system, I mean in the solid phase, you have a limited amount of particles with which one particle can interact with. And so in this so the algorithm now scales like n, but clearly we have to take into consideration the problem of finding which particles are within a certain radius of other particles. And also another things to consider is that the particles should not interact with themselves or interact more than once with other particles. And so either the system is large enough, or we have to take the the cell size less than say 2 RC. And if the system is large enough, we have to consider that a particle sees multiple copies. If we use a periodic boundary condition, a particle can see multiple copies of the same particle in different cells, and so we have to consider only those that are nearer to the particle into consideration. So, for instance, in this case, the black particle should interact with this copy of the J particle and not with with this one or this one or this one. But this is a problem only for periodic boundary condition. We can use a fixed boundary condition, and so that we do not have this problem. So let's go to the simulation. We can open the Lennard-Jones molecular dynamics simulation, and okay, we can. I adapted the model that is in the model library, so that the interface is the same, but the computer code is different. And so we can set up either using a configuration near to the rest configuration or a random configuration. We can fix the density and so the number of atoms in our system. We can also fix the initial temperature, which is just the kinetic energy of the particles. And so clearly this is a quite slow system, so we have to lower the refresh in order to can see actually the particle that moves. You can see that the energy is conserved with the oscillations due again to the algorithm and to the fact that when they interact, clearly the energy is conserved, but we can have some small variation. What is important is that we have a conservation of law in the long limit, and we clearly can follow the movement of the particles, and we can also decrease the temperature. Now you see that energy is lowering. Actually, this means that I am multiplying at each time step the velocity for a certain quantity which is less than 1. And you can, in this way, we can explore what happens for different energies. Let's have a look at the code, which is clearly more complex because I have to take into consideration the offset of the potential, number of atoms, the representation of histogram that we shall study in a following lesson. But the main point is essentially the same as before. We advance the position of each particle, which are particles. We compute the new coordinates. Here we check for boundary condition. In case of a boundary condition, we have to reverse the velocity, the appropriate velocity, and to move the particle so that it stays inside. And then I ask Tata to move to the new position. And finally, I have to compute the forces. And so for each turtle, I memorize the position of this turtle. So these are the temporary variables for computing the forces, and I also memorize the ID of this particle. Then I ask all other turtles in a certain radius. So in this case, I don't have to check explicitly those that are inside the cells, because this is done automatically by NetLogo. When I ask in radius, it simply uses the patches in order to compute which are the turtles that stays in a certain radius. And so I rescaled the epsilon and sigma, so the forces, in order to have a radius equal to 1, but I could have done differently. And then, so all other turtles computed the distance, so in x and y, with respect to my coordinates, the coordinate of those that have asked doing that. This RC is the rescaling, so that I can use radius 1, and this is the rescaled radius. So these are the distance in the real coordinates without rescaling. This is the square of the distance, so because I've seen that I can recompute the potential in order of the as the rescale the distance to the power -2. This is essentially what we have seen as W in the previous slide. This one. This W here is Rm2 in this code. And okay, so this is the force. Then this is the energy with the two possibilities if it is inside or outside. Then the third Newton law. I don't need it here, but I could also have halved the computation by exploiting the fact that the action and reaction are the same, but it's not worth doing that. And finally, having computed the increment of the force with respect to all others and having summed it into my fx and my fy, I can finally set my force, the force of the turtle who started the computation, to this, and then I can finally update the velocity with the new forces. So you have seen that computation is so a bit heavy, and then I can compute energy, plots which are not considered here, and that's all. And so I can let it go and explore what happens for different values. I'm lowering the temperature now. I can stop the lowering of temperature and let the system evolve for a certain time step, and I can see that while we leave it evolve, we can go back to the presentation and see that what happens for different energies, and we see that actually at low temperature it goes into a crystal state that behaves like a solid, possibly with thermal dilatation, since the potential is not harmonic. It can give origin to dilatation by temperature, and we shall see when we shall deal with the kinetic theory that energy should be distributed in a certain way, and actually this is what I see in the simulations. And at low temperature, essentially, so at high temperature, it essentially behaves like a random motion, an ideal gas, excuse me. And if I track, I shall show in a minute, a single particle, it will follow a random, so a pseudo-random walk at a Brownian motion that we shall study in one of the following lessons. At energies near zero, we have essentially formation of droplets, which essentially is what is done by a liquid when start to change the phase. clearly we have no density, no gravity here, so we don't have a surface separation, but we could introduce it. And so let's go back to the screen here and see that actually you see that the gas starts to condensate. You also notice that the simulation is quite low. I have just 100 atoms. Here, this is due to NetLogo features, because if I run a virtual program written in C language, it is much faster than this. And okay, so this is, for instance, I can lower temperature. Let's see. And see, okay, I can lower temperature so that I can reach very, very low temperatures, and the system essentially stays together, eventually oscillating a bit, but it essentially behaves like a solid body. Okay, just to conclude this lesson, I mentioned another well-known integration method, which is the Runge-Kutta method, which is a fourth order. I mean that in this case the force is computed 4 times for each time step. And for instance, you have seen already here with the Verlet algorithm how slow is the computation of forces. And so the method is an iterative method. I computed the first force at a certain point, then a starting point, and then I increase a bit the time, increase a bit the position, and I compute again the force here, then again and again, and finally I compute a kind of averages of these computations, and this is the new. This gives you the new position of the particle, and I shall show, not now, but in a future lesson when we shall speak about the dynamical system, how use this in NetLogo. And I only anticipate that since this is the scheme for just one variables, and I have to repeat this for say at least 2 variables in 2 dimensions, I mean x and v, the velocity, or 3 variables in 3 dimensions, then it is done by storing the state in a list, xy or xyz, in 2 or 3 dimensions, and then I have to iterate things, and so define how to compute the derivative for the 3 dimension and report a list of derivative of 3 dimension. This is for a special model that we shall see in a future lesson. And be prepared to study how NetLogo deals with maps, because with say essentially list by using the map. Map is a way of applying a certain piece of code to all elements of the list. So essentially, this is the representation of this step here, where f is the computation of the derivative. So in NetLogo it is, okay, this df tn state n is what I get here in order to compute the derivative at time tn at point state n. State n is the list x, y, z of the coordinate of the particle. Then, so this gives me a list of derivatives, and I have to multiply them by h, which is delta t, and I use the map in order to apply this function. So x, which is one of the elements of this list, goes into h times x. So it is essentially multiplication of the list by h. And this is stored into K1. Then I repeat this map, and so I get the four elements that compose a Runge-Kutta step, and then I have to multiply them separately by 6 or 3 here. Then I get the result of this, which is a list of lists. I use reduce in order to sum this list of lists into a single list. And finally, I use again map in order to increase the state of the single particle by this increment. So essentially, this is the xn plus this. So it's not so easy to implement this in NetLog, but hopefully it has been already done. And so we shall make use of this algorithm in the future lesson. I put it here just for completeness. That's all for this lesson, and see you again.